Good afternoon and welcome everybody to this actually first of the daylight group sessions since we went into sort of COVID hibernation some time ago. So it's particularly gratifying to see that so many people have signed up for this already. And this will be the first of a series which will be initially, for at least the next few months, exclusively online, but of course we are hoping to be back to a physical event, or at least a hybrid, before too long. So firstly, I'd like to thank Jada Sola from CIBSE, who arranged everything, and also introduce Martha, who is our new Daylight Group Secretary. Oh, perhaps I should say my name is John Medalevich. I'm the chair of the Daylight Group as well. But Martha, please, if you'd just like to say a word or two about yourself.
Hello, very nice to be here in the first online event. My name is Marta Vlaquito. I'm a senior sustainability engineer in Bureau Happold. Yeah, that's more or less me.
Short and sweet. Right. So our speaker this afternoon is Paul Kenny from University College Dublin. Paul is a lecturer at the School of Architecture, Planning and Environmental Policy at University College Dublin. He has been involved in the building industry for some 30 years, first as an engineer with Mrp, then as a consultant and researcher working with colleagues on EU-funded research projects, and later as an academic at UCD. Paul has a sustained interest in environmental building design and more recently in healthy indoor environments. His specific interest and the subject of his recently completed PhD is in a better understanding of the spectral interaction of daylight with the indoor environment as part of a more complete design of healthy internal spaces. Now, before we go on to the presentation, I need to give a little bit of a full disclosure. So I was the lead supervisor for Paul's PhD. My co-supervisors were Dr. Eleonora Brembila, now at Delft University, and Professor Christina Hopfer, now at Graz University. Paul worked remotely entirely. He's based in Dublin. And this work was done part-time over a period of, I think, 4.5 years, something
5.5.
Yeah. Well, so and the second thing I really have to disclose is actually Paul did not give his supervisors much to do other than read the material as it appeared. So Paul, I should say this presentation, it'll be somewhere between 30 and 40 minutes long, and we'll have plenty of time for questions afterwards. When the Q&A session begins, all your microphones will be switched on, so you will have access to those. So please use either the microphone or the chat box when we come to the question session. But until then, I will hand over to Paul. Oh, I should just mention this session is of course being recorded, and it will be available on the CIBSE website on the Daylight Group channel. So Paul, over to you.
Okay, John, thank you very much, and thanks to you, John, and to the CIBSE Daylight Group for inviting me. I'm going to go straight to screen share if I can. If there's any difficulties in seeing this, please do flag it with me. So as John said, this is a kind of a snapshot of a PhD that I recently completed under John's supervision. What I'd like to do today is to give you, I suppose, some of the highlights of different parts. It was really of two parts. There was the development of a methodology, which was implemented, and then creation of data set and the analysis of that. So what I'd like to do is really just outline very briefly the context behind the research area, give you a flavor of the objectives we put in place, the developed methodology, talk a little bit about the data set that was derived from it, have a quick look at some of the results, the analysis of the results. They are extensive, and so at the end of the presentation, I'll give you the link and a QR code to scan if you wish to the completed PhD, which is on the Loughborough University Library repository. And you can look at the detail there if it's of relevance or of interest to you. Now, being involved with light, you will most likely know and have heard already that we now understand that illumination, receipt of the eye, has both visual and non-visual effects. And what we're concerned about here is that non-visual effect, and particularly in the circadian entrainment of our physiological systems. And that is really the daily resetting of our clock. Our clock is running in approximately about 24.2 hours, but that's a little off from the solar cycle. So this resetting becomes quite important to our physiological and psychological well-being. Now, the mechanism by which this is achieved within ourselves is through light stimulation of what we now refer to as the intrinsically photosensitive retina ganglion cell, a new cell that was discovered, well, confirmation of its discovery a little more than about 20 years ago. The process as mapped out, and I've included this particular image from a relatively recent publication in LR&T, maps out quite a complex process between source of light through to the response of an occupant within a space. This research is concerned specifically with daylight and daylight only. It is not considered artificial light sources, and we're not considering the occupant other than the fact that what we're looking at in terms of results within the space will impact on the occupant. But what we're really looking at is the space itself and the interaction with daylight as the light source. So to try and illustrate briefly the scenario that was created to set out the methodology around which the methodology was set out, what we're looking at really is what happens to daylight as it moves from source to destination being the eye of an occupant within a space. So what we have are sources outside. We have direct, we have diffuse, we have the reflected components passing through an opening, which will have glazing, into a space which will have various parameters which may or may not, or to one extent or another, affect the spectral distribution of light that eventually resolves and results at that point of observation, and in this case, point of measurement. At the moment, there's been very little analysis of this particular scenario, partly because daylight is seen to be very complex, and certainly as we progress through the research, it certainly proved to be so. So what was really the first step was the development of an appropriate methodology. What we needed to do is create a system, an apparatus, by which we could actually begin to measure and record over as long a period as possible what was happening. There was in the literature, after a review, not a lot of precedent or recommendations. One particular study had been done, but in a very limited way. Otherwise, we're relying on a number of technical guidance documents from CIE and others. So the first step of the process was the development of an appropriate methodology by which we could measure the spectral, now what I'm calling microclimate. I'm really talking about that kind of enclosed, bounded space that we're concerned with, the indoor space, for daylight conditions. I'll just emphasize that this is just daylight, no artificial light source. Based on that methodology, an apparatus was built, and that was then switched on and left run, monitoring spectral conditions within a space over a period of time. And that time was within the limits of undertaking PhD. It ended up being about 8 months. From this, we generated a representative data set of a range of conditions for various parameters. The next step then, of course, was to analyze that data set and to look at the relative effectiveness of the variables that were considered in the study to see what was happening within that microclimatic or spectral microclimate. And then finally, to test the underlying assumption, and it still is the assumption that the spectral properties of daylight, both internally and externally, are strongly dependent on instantaneous sun and sky conditions. So we really were starting from ground zero as such in terms of developing methodology. Now, what I want to do is I'm going to give about a 50-50% method and results. So what I'd like to do is take a little bit of time just to look at the method, because that will also give a context to what the data set represents. And I think this is important for any future use of that data set as well. So I'm kind of jumping ahead to give you this is a schematic of the system that eventually was developed and tested and developed. And what I'll do is I'll then step back and look at each of the components and how they all came together in this system. So computer modeling really didn't provide the means by which you could look at real daylight conditions and all its variability. So it had to be a real space. The availability of a full-scale one-to-one space wasn't available to the research, and it in itself would have had its own limitations. So a scale model was the chosen representation for the space put under test. In that were located 4 spectrometers, microspectrometers, directed 90 degrees apart, 3 looking at the internal wall surfaces, and a 4th looking at a full wall to ceiling, side-to-side glazing. You'll also see that there's a small fisheye camera placed looking into the space. And from this was taking photographs, but also luminance maps of the space. And these were used as a source of reference. Simultaneous to measurements being taken internally were measurements taken externally. And this was important for this research because in a way, we're not looking for absolutes, we're looking at the relativity. We're looking at, well, what's happening outside and what's the consequence inside, and the transition between the two was really what we were trying to get an understanding about. So a 5th spectrometer was focused outside, and next to it then a 2nd fisheye camera. All these devices being operated simultaneously, so everything was captured at the exact same time. The controllers used were small Raspberry Pis. If you don't know these and you're into this kind of experimentation or have a use for it, an extremely robust and reliable device. So in total, we had 8 Raspberry Pis in operation. 1 was the controller, which synchronized the whole measurement system. Some processing was done at the Raspberry Pi level. Others, data was transferred to a server where post-processing was carried out, HDR generation using radians and such. So in the end, it became quite a complex and involved system with a layer of software then to manage the whole thing. So that's the full context. What I'll do now is just step back and give you details that make up that system. So the first is the location. So the location was south of Dublin city centre on the campus of University College Dublin, and specifically my own office. So you'll see the location pointers up in the corner. 2 windows facing southeast-ish were used. One for mounting the scale model. Part of the window was replaced and the model mounted there. And the second for mounting the external sensors. And we'll have a look at those briefly. You can see the latitude and longitude, 53.3 and -6.24. So time-wise, we're about 25 minutes west of Greenwich Prime Meridian. So the first fisheye is a portrayal of the scene that is seen outside, the sensors that are looking outside, and of the scale model. The middle image is a plan representation of the direction of focus of the spectrometers, the 4 internally, and SP05, the one focused externally. And then the stereographic sun-path diagram is really just to give a sense of how that room was orientated. So it wasn't a convenient south-facing room. In actual fact, later on, when we're looking at the results, that actually turned out to be an advantage. So the room's azimuth is about 125 degrees, so a little off southeast. The yellow patch that is seen plotted on the sun-path diagram gives a geometric representation of the view of the window from the point of view of spectrometer number 4 looking out the window. And then there's a gray area shown in the sun path diagram. This represents the sun path that was no longer visible to the room. So because of the orientation, the sun path later in the afternoon was not visible. And once again, that proved quite useful in the interpretation of some of the results. Now, it looks quite basic, but in actual fact, this particular construction proved resilient and flexible throughout the whole research. It's essentially a box. Within the box were placed panels on the wall. These were simply Velcroed. The panels were very carefully finished in a range of colors. We'll talk about those shortly. And the whole thing could essentially be deconstructed and reconstructed in a matter of minutes. So the whole thing became very accessible and easy to work with. Position, reposition, and such for calibration of sensors, anything that was required. The image on the right-hand side will show you the whole apparatus closed up and in operation. So the space and the dimensions of that space were somewhat limited by the window that was used for mounting the model. But in the end, it was a 1:7 scale model, equivalent of a room of about 3 meters by 5 by 8 deep. So the deep room was relatively deep, but again, this was something that we wanted to have a look at. Now, the first variable to be considered, and this is coming out of reviewing the literature that is published, even within computer models, the color or the spectral reflectance of surfaces within the model are continually seen to be particularly important. But other than one particular study, which considered wall colors under only clear skies for a very short period, no other research had really looked at the differences between colors. So what colors to choose? Again, in almost every step of developing this methodology, there was very little precedent upon which to build. So a publication was published in 2012, where a range of colors were proposed that were equiluminant. And the use of these at least meant that the reflectivity, broadband reflectivity of these colors was in and around about the same. So mixing paints proved a little challenging and rather expensive after multiple attempts, but you can see under the LRV, this light reflecting value, that the reflection value of the red, blue, and yellow, the specific colors used in the study, are close. The white, about 85%, and the gray, which represented the floor, about 27. Now, again, going out, looking at studies, looking at light reflection values published by manufacturers of floor materials and such, varied hugely. But a lot of studies would have used between 25 and 35% to represent floors. Throughout the study, the floor was kept consistent. It was the same floor as was the ceiling. So the ceiling was white and the floor was gray. And only the 3 walls internally were changed in the different scenarios. These spectral reflection profiles were generated by Fleetwood Paints in Cavan in Ireland, the manufacturers of the paint, and they used a benchtop spectrometer to derive these. And we'll revisit these later on when we're looking at the results, but these particular spectral profiles are important as well in interpreting the results that come out. Another consideration was the potential spectral reflectance of the external environment. So as you saw from the fisheye, while it is outside, the scale model is a combination of building, vegetation, and then, of course, the sky. Now, this particular study, I won't dwell on it, but it's been published in 2008 at the CIBSE Technical Symposium. It's a short exploratory study I did as part of this, where I went into Dublin city centre and took a range of spectral measurements in different streetscapes and older buildings, newer buildings, different materials. And the conclusion was that really, once your scene or your point of view within a space can see sky, a luminous sky with or without sun, it is the dominant source influencing the spectral distribution. And the reflected component from other ones really did not change or modify the spectral distribution to any detectable extent. And so from this point of view, that change outside was not considered. And given that it was consistent throughout, in terms of a relative study, it wasn't a significant factor. The other dimension looked at in that short study was also the street width to height ratio, to see if in that any detection or anything could be detected. And again, it supported the conclusion that it wasn't a significant factor. Now, this was probably one of the more important categories to define, and that is the sky. So one might think you start with the CA classification of overcast, intermediate, and clear. But when we're looking at real skies and we're looking at essentially a random distribution of cloud on a blue sky, the CIE sky types don't really help. So I borrowed a little bit from the Octa method and developed a scale from 0 to 10 called the sky cloud fraction. And it simply is a percentage of cloud relative to the whole area of the sky visible from the model itself. And on that basis then created this scale as presented in images, and on the right the ranges. So 0 would be 0 to 0.5%, then 1 through to 9 covers a full point, and then 10 being completely overcast, 9.5 to 10. And so this was used as a kind of a category for analysis later on, to be able to look at what, if any, effect the sky cloud distributions and proportions might have. These results were also generated automatically. We wrote a small program to analyze images taken at every measurement instance from which to derive an SCF factor, and this was associated with each reading set. Now, this was an odd one. During testing before full monitoring, it was clear to see that the internal environments within the scale model differed significantly. So in those depictions on the right, that one on the top is clearly a sky cloud factor, a fraction of 10. It was a fully clouded sky, and the result internally is a diffuse environment. That on the bottom, we have a direct component, direct solar component, and so it's easy to see that difference between shadow and non-shadow, very, very carefully defined and tightly defined, that boundary. The middle condition was less clear and quite variable. And at the time of pre-testing, it was difficult to know whether or not this was significant as regards to the spectral monitoring. It wasn't at the time easy to come up with a software solution based on imagery to actually do an analysis. So manually, at the end, through interpretation of these images, classification with 3 factors: no sun, sun, or mix, that middle condition, was assigned to each reading. Again, not really knowing whether it was significant or not, but in actual fact, in the end, it proved to be quite informative. It is a factor that only relates to the internal environment as opposed to what is happening externally. So in the end, inside the model, this is a depiction inside the model, 4 spectrometers were mounted at the center of the model, both vertically and horizontally. And you can see the small insert, the spectrometers on the optic fibers. And these were accompanied with an Illuminance sensor paired with each spectrometer, and I'll explain why that was in a minute. And then the fisheye images on the right-hand side, a representation of the hemispherical field of view that would be seen from each of the spectrometer positions in the room. So it gives us an idea of exposure to the external view, percentage of colored wall, white ceiling, and gray floor. The external unit was mounted on a replacement window again. In this case, a 5th spectrometer focused outside, paired with a fisheye camera. And so again, the 4 sensors inside, the camera inside the model, the external spectrometer outside with the fisheye camera, all synchronized through a controller, a master controller, capturing images every 5 minutes, essentially, for the internal and external environment. What was important, should anybody be involved in any research like this, was to avoid condensation, so that the images as well as the spectral readings weren't affected. To achieve this, the back of this unit was left open to the room for air circulation, and a large amount of desiccant placed inside. And I have to say, over the 8 months of monitoring, which included through the winter, no condensation occurred. So it was a simple but a practical solution. Now, the most important sensor of all in this research was, of course, the spectrometer. In terms of specifying, in searching for an appropriate unit, we were looking for a spectral sensitivity range, obviously within the visible spectrum, but at least 380 to 780 nanometers. As we were developing something quite new, it wasn't something off the shelf, we needed an application programming interface. It wasn't quite clear to what extent software would have to be developed as we went along, but quickly realized that a degree of software development was going to be required, so that element was very important. It had to be small. 4 of these were going to be placed in the model, so they in themselves shouldn't be interfering in any significant way with what's happening in the model. And given that it was self-financed, cost was a hugely important issue. So having reviewed the market and looked at a whole range of devices on the market at the time, the one that had emerged as an obvious choice was made by the company known at the time Ocean Optics. It's now been renamed Ocean Insight. It was an SCS-VIS. These are a miniature spectrometer, very robust, very reliable, and they were being marketed at the time as part of a software development or development kit married to a Raspberry Pi and with a battery pack. So one of these was purchased, experimented with, and quickly proved to be very effective. The software that came with that kit was not deemed suitable, so essentially everything that controls the whole system was written from scratch. Now, what became very important in the development of the monitoring system was looking at potential sources of error, and in particular with the spectrometers, sources of noise. So these had to be eliminated as far as possible. All recommendations suggest that if you are not actively cooling such a device to a controlled temperature, that the temperature be kept stable. So at least the noise as a result of temperature can be characterized and eliminated. Quite often, when taking spectral measurements, a range of measurements were taken at a number of integration times and an optimum chosen, optimum being typically between 70 and 80% of the maximum photon count of the sensor. Given the nature of daylight and how rapidly it can change, and changes of 1000% over 1 or 2 seconds were measured during this period, what I needed to achieve was a single measurement at all 5 spectrometers at the same time. And that in itself was well, it was an unknown at the time. The way this was achieved was to characterize the relationship between integration time and illuminance at each of the spectrometers, and remembering that each spectrometer is looking in a different direction, essentially to a different environment. So the illuminance would have been markedly different at each one. This proved, thankfully, possible. So a relationship between integration time for the spectrometers and illuminance was characterized and coded into the software, the control software. The other then was, of course, those collective sources of noise and integration time. The longer the integration time was extended, the more noise there would be. Again, this proved to be a linear relationship, and so it was very easy to include in the software in terms of applying calibrations and control. So we're back to this. So all of that collected resolved into this system as is portrayed here. Now I should say these slides are going to be provided afterwards, so if anybody is interested, you can go into the detail as we go through. In particular in this slide, not expecting anybody to pour over this, but behind the hardware, of course, was a software architecture that had to be developed from scratch, and this was achieved. The Raspberry Pi runs a Linux operating system, so it's a flavor of Unix, and based on the Bash command line language as well as Python, a wide range of scripts were developed and basically put together in this flow architecture. So we had a startup routine for each day, which is essentially timing 2 hours after sunrise, and that was different for each day, of course, and a shutdown procedure. Once the system was started up, it entered into a 5-minute loop. For every 5-minute interval, each of the 5 spectrometers were activated to take a reading. Calibrations applied, and out of this, an absolute irradiance measurement was derived from each one. The cameras were simultaneously activated as well, with images, HDR images, and from these using radiance with vignetting control and luminance mapping. So all this data was brought together, and collectively I refer to it as a reading set. So it's a collective of readings of 5 spectrometers and 2 cameras collected together. So this is a representation of that data. So we have the data in terms of raw counts from each of the spectrometers, the converted absolute irradiances, and then the imagery, but visually represented for every time instance captured. This is, I suppose, the visual representation of that data. So we have an external photograph and a luminance map, an internal photograph, an internal luminance map, and these were used largely for reference in interpreting what might be happening at any one time. And then the plot. So the plot is all 5 spectrometers, noting that the axis on the right is for the external measurements, and that on the left for all the internals. And then across the top of that, we have a timestamp, the SCF, so this is the sky cloud fraction, and in this case is about approximately 40%. And then the wall color that was in place at the time of the reading, which in this case is pink. So this is a visual representation of the data that was collected. So across the period of monitoring, which in totality was about 120 days, 13,331 individual reading sets were collected, as represented in that previous slide. From that, a subset of 2,689 were chosen and are just as distributed in the tables on the right-hand side. And these were to represent all 11 sky conditions as defined by the sky cloud fraction for each of the 4 colors considered in the monitoring, and for each hour of the day, typically between 8 in the morning and more particularly about 4 in the afternoon. So again, the distribution, trying to get it as even as possible for each of the 4 colors. Now, the resultant data set, the collection of the various reading sets. The data collected included 4 categorical values, and these would have been the 5 spectrometers, and these in themselves indicate the view or the orientation of those sensors. The 4 wall colors, white, yellow, blue, and pink. Cloud fraction on the scale of 0 to 10, and then that internal sun condition, whether it be no sun, sun, or this mixed condition. Together with that data, and derived from the absolute irradiance, were the other variables that are listed there. So luminance irradiance, CIE 026 derived metrics, circadian stimulus, circadian light, action, circadian action factor, which is M over P, melanopic photopic ratio, correlated color temperature, and so on. So I created 2 data sets out of this. The first was simply just those results. The second being the extended, including all absolute irradiance values for each of the readings for each spectrometer on a 1 nanometer interval. It was a much larger data set. So in terms of processing data for interpreting the results, the smaller data set was faster in processing. So this came out as the result of a CSV file, a comma separated file. So this small table is just a snapshot. This is one single reading set represented in the data set without the spectral data then. So we have timestamp. So each reading set would represent 5 lines of data in the data set, 1 for each of the 5 spectrometers, together with the wall color, the sun cloud fraction, sun condition, and then the various metrics derived. Now, the metrics were derived from a combination of sources. And I've listed some of the software that was used here, should anybody be interested. Unapologetically prompting or supporting open source. Everything that was used in this research was open source, and it's just a nod to those people who contribute to that software. So the Python environment was the collective environment that was used in terms of programming. LuxPy has been covered in LR&T previously, and this is a application library, programming library. And from this, you can calculate directly the circadian stimulus and circadian light. More recent versions can actually connect directly to an ocean optic spectrometer and take the reading. So it's actually becoming almost a simpler solution than I've had to deal with. Color Science is another Python library for calculating correlated color temperature. There are 4 methods included in that library. And it outputs a very high quality graphic as well. So it was a superior library to choose. NumPy, SciPy extending the potential of Python for analysis and calculations. Matplotlib and Seaborn are for graphic output. And then Pandas is typically used as a library for data analysis. So those in combination with a number of scripts written were collectively used for programming the monitoring system and for the analysis. Where metrics were calculated based on my own scripts, I was able to use toolkits from CIE and from the parties who publish circadian stimulus and circadian light to do a quality check to make sure that they were accurate, and thankfully they were very accurate. Now, that essentially is essentially the method and the data set collected. Before moving on to the interpretation of the results, I'm just going to briefly talk about the metrics themselves, because while the research didn't set out to critique the metrics, it became necessary to look into them to understand exactly what they were trying to represent and how that might be used to interpret what was happening within the model under the different conditions. At the core of all this really is what efficiency response function is appropriate, and this story is one that is evolving. It's still in development. It's not resolved. It's not conclusive. What we have on these 2 plots are a series of points, the dots, the triangles, and that solitary X. This is the data that came from research from Brainard and from Taupin from many years ago, upon which most efficiency response functions have been based. The first being by Gall and colleagues, and this was quite a close fit to the data, and this became part of a very early DIN standard in Germany for the study of circadian light. That on the right was published by Ray, Figueroa, and colleagues. This was an attempt to be more inclusive of all the functions of the eye in representing circadian response, not just from the point of view of the response of melanopsin. The response of melanopsin became the focus of the more recent CIE standard, CIE 026, published in 2018. And that is the blue curve that you will see in the left plot. In some older publications, this is often abbreviated by using the capital C in brackets lambda, so the circadian response function. In the CIE standard, the notation has changed somewhat and is now being denoted as small s subscript mel lambda. But we'll see this as we move on. So there's a range, and depending on which metric you use in the method, you will use a combination of these. And so interpreting the results is not exactly a comparison of like for like, and this is a complicating factor in itself. So the metrics considered at the outset, having gone through quite a range of them, boils down to those that are most widely used, but also that potentially were the most informative. So the melanopic photopic ratio is one. We'll look at that briefly. Daylight efficacy ratio, this is coming out of the CIE standard, as is the equivalent daylight illuminance, EDI, and this is the successor to the equivalent melanopic lux that came out of the paper from Lucas some years before, but it's the same core group of researchers who are behind the CIE standard as well, largely. And then, of course, that family from Ray, Figueroa, and colleagues, circadian light and circadian stimulus. Now, I don't want to dwell on the mathematics of all these, but it is, as became very apparent in this study, really quite important to understand the mechanics going on behind each of these methods. The Mrp ratio, at the moment, there are 4 methods of calculating the Mrp ratio. They all relate to each other in that they can be converted from one to the other by application of a simple multiplying factor. But the problem is, in the literature, it's often the case that an Mrp ratio is published without reference to the method of calculation. And so you can understand how misinterpretation might result from this. And I think it's important in the application of Mrp that it is very clear how it's being calculated. Now, some have argued, including Mark Ray, that the Mrp is not indicative of circadian potential to somebody within a space. And I would absolutely agree, but it is very useful when looking at light sources. And so if you think about a space as a recipient of daylight and how it's transformed, one could extend that and consider it a source of light, at least to the occupant. And that's the approach I took. So ACV, and I don't want to confuse people, but ACV is the action factor that was published by Gall along with their response function. And it's very simply a melanopic weighted irradiant quantity with respect to a photopic radiant quantity. Simple as that. It's probably the most simple calculation of all the Mrps. And I've included just some examples using the D series, the CID series. For an equal energy source, the Mrp using this method comes out about 0.82. So that is the first of the 4 Mrp methods. The equivalent daylight illuminance, this is the formula used. It's a melanopic weighted irradiance divided by efficacy of D65. And so D65 is used throughout this standard as a reference. The other relation coming from that same publication, the same standard, is the daylight efficacy ratio, the DER. Now, to all intents and purposes, this is the 4th most recent calculation method for Mrp. But in this case, it's referenced against D65. And so as a first look at the data, something that jumped out very, very early on when looking at these metrics. What I'm presenting here is data collected at spectrometer number 1. So this is looking at one of the sidewalls inside the model. If you calculate and plot the daylight efficacy ratio, according to CIE, using D65, you'll get the plot on the left. So these are the internal spectral measurements. It's an Mrp ratio, essentially, with a reference to D65. And so these are actual measurements relative to this D65 standard. The same points plotted where I'm substituting for D65 the actual measured external irradiances gives you a very, very different plot. Now, I'm not trying to say that the daylight FC ratio is not appropriate for use, but what I would say is in the case of using it in terms of real daylight conditions, I think it is important that instead of using D65, external measurements are used, because you can see how the interpretation of those two plots could give you very, very different results. The flatness of the points in that second plot is something we'll come back to, and that was probably the first of many very interesting results that came out of the research. Comparing these two different methods of calculating M over P, so the one on the left is the daylight XC ratio, and the one on the right, the action factor, according to Gall, much more simple. The plots, to all intents and purposes, are the exact same, except one is shifted relative to the other. In actual fact, conversion from one to the other is simply the application of 0.905 as a factor. And so this is just really to illustrate the point that the four methods of calculating M over P are relatable. But what's important is stating very clearly how that M over P calculation has been carried out. Now, we're definitely not going to dwell on this. This formula really, I suppose, illustrates very clearly the attempts that Ray and Figueroa and others have tried to capture that full circadian entrainment potential of the eye, including all photoreceptors in the eye, as opposed to simply looking at a melanopsin response. Circadian light is calculated depending on two specific conditions, and from that, the circadian stimulus is calculated. This is a metric that's widely used in both research and in practice, particularly in the United States. In this study, it was found to be somewhat limiting. So some of the illuminances we measured inside the model were quite high, particularly when the sun was quite low and clear sky. What you can see on the plots is the first thing to note is as the plot reached the maximum of 0.7, and 0.7 is the highest achievable scale in the CS metric, all the results essentially compressed and plateaued at in and around 0.7. But more particularly, what I've done here is subcategorize these plots for the four wall colors. Only the yellow wall really separates itself from the rest. The other three colors, even though they have quite different spectral reflectance profiles, are clustered. My conclusion was that really circadian stimulus works well first with lower luminance levels. It might be typically found in deeper spaces or with low light. But it didn't seem to have the sensitivity to differentiate between the wall colors, even if those wall color spectral reflectance profiles were markedly different. And so the CS wasn't used in further analysis in this research. I see time is moving on. I'll pick up the pace. This is a plot of three metrics. So we have equivalent daylight illuminance. You can see the linearness and clustering for each wall color. The CS, as I said, it plateaus and doesn't really separate. But what you can see with the action factor, or M over P ratios, you get a much more detailed and informative distribution, and the colors are more separate, and that became more interesting. So the M over P ratio of those existing metrics became quite useful. A lot here. What dawned on me as I was going through the metrics was, in all of these metrics, there was always a photopic component. But as we're speaking about a non-visual impact, and if you take the argument of the CIE group, suggesting that melanopsin is most indicative of the circadian entrainment potential of a space, then why not have a melanopic only metric? And I just threw these into the research just to see what might come out of them. And whether you like the term or not, one relationship that has proven quite informative was a melanopic, and put in brackets, daylight factor. And simply because we have the external measurements measured at the same time as internal, we can relate the two. What's happening inside relative to outside, because that is essentially at the core of what we're trying to find out. What are the transformations and why are they happening? So we've included these relationships in the research. So first, external results using correlated color temperature, a metric that I'm sure everybody is quite familiar with. The external results fell almost spot on onto the daylight locus, as expected. There really are only two other groups of data out published, one from Colorado, one from Madrid. They're slightly above the daylight locus. But remember that these values were taken looking at the horizon. So it was a kind of a vertical irradiance measurement. And as far as I'm aware from reviewing the literature, that hasn't been published up until now. There is a small tail of data, which I haven't yet quite explained, but the linear nature and the number of points suggest that there's some phenomenon happening at a particular time of day. They're not errors, and I'm still trying to figure out exactly what that is. The image on the left is simply just a distribution, but what it points out is that D65 in this case, throughout this monitoring period, was not the most representative of the sky correlated color temperatures, more in the range of D55 to D60 if you wanted to introduce another one. Okay, these are simply plots of the external data. I want to have a look at what was happening to daylight outside before we began to look inside. We have illuminance, we have equivalent daylight illuminance, and then the M/P ratio as represented by the action factor. Illuminance and equivalent daylight illuminance are very closely related in terms of pattern, albeit that there's one is slightly lower than the other. The M/P ratio is quite interesting, and these red lines that have been superimposed are simply just matching up the trend of the medians in these box plots. But the M/P ratio is quite interesting in that we had initially expected it to be more variable, but other than at the lower SCF range, which is indicating a clearer sky, it's actually quite flat, suggesting that the variation in melanopic photopic light quantities across a wide range of sky cloud conditions actually doesn't vary that much, but we'll return to this briefly. Correlation between illuminance and equivalent daylight illuminance, again, a simple factor. And so the conversion from illuminance to EDI, according to this correlation, is one that could be easily achieved. Again, these are external readings. So what I've done here is I've basically looked at that previous graph, M/P, and I've subcategorized it by that internal sun condition, with sun, without sun, and that mixed condition. And what can be very quickly seen, looking at the blue on the left, we can see that when there's a direct component under that Y sun condition, there's virtually no change at all in the M/P ratio, irrespective of the sky condition outside. The mixed condition, clearly the direct component within that is still having a strong influence. It's slightly higher in terms of M/P value, but again, essentially no change across those sky cloud conditions. Where you do see a change is where there is no sun present. So the direct component is now gone. It's entirely diffuse component. And as might be expected under SCF of 0, that is a clear sky, there's a high melanopic component relative to the photopic. And so you get this gradual decrease across that scale as you move towards a more cloudy sky. And this is something that's quite interesting. This was not necessarily expected, but it does suggest that in this case, where the direct component is present and has influence, it dominates the spectral distribution and that M/P ratio within a space. That on the right is the same M/P ratio plotted against illuminance. This is not an unusual curve from published studies of luminance sky luminance. I've superimposed here the daylight series scale. What we can see is that lower luminances, and again subcategorized by the sun condition, there's a much higher M/P ratio. But as the illuminance increases, and this is only achievable through a greater and greater presence of direct component, the M/P plateaus. And the interesting thing is it plateaus at about 5,250, 5,300 Kelvin, correlated color temperature, of course, closely associated with the CCT of sunlight. So it's quite interesting to see this pattern emerging from the results. Across the day, and this is one of those melanopic only measurements. It's melanopic irradiance relative to the total between 380 and 780 nanometers. There is a gradual increase throughout the day. That latter time slot, that 3 o'clock to 4 o'clock in the afternoon, there's no sunlight present because it's now gone behind the building. And so we can see at that 0 sky, clear sky level, there's a higher melanopic content. But there's a very slight increase throughout the day. But again, surprisingly, very consistent, irrespective of sky condition. A plot of the melanopic only irradiance within the space, and I've included the external one at the bottom just as a reference, really follows where the sun might be. And this hasn't been, this is relative to these images in on the right. Again, the orientation becomes relevant here, and the same rules are applying here to regular daylight design rules of thumb. There's nothing specific to spectral properties of light in this. Where it becomes interesting then is when you look at the melanopic only ratio. So this is the melanopic daylight factor. Again, the difference between melanopic content inside and out relative to sky condition doesn't vary that much, but where you do get a change is the solar angle. And I suppose it's essentially how it's interacting with the reflective spaces or surfaces internally in the model that you will get the variations. So you get a small dip in all values in around the middle of the day. Because of the orientation of this would be between 12 o'clock and 1 o'clock in Dublin. SPO4, looking out of the window, its results were quite unique. The other three were quite similar and quite interpretable collectively. This had a view of the outside. It became the dominant light source and really did have a strong influence on the values. John, do stop me quickly if I'm running way over. Just to revisit these spectral reflectance patterns, it's important. In actual fact, a lot can be deciphered just simply looking at these with respect to a space. But one can see the white and the grey are quite level right across the wavelength range. Blue obviously high at blue, yellow deficient in blue, but then picking up towards the red. The pink is unusual in the sense that it's quite strong at the blue end, then dips and then picks up again. But these are important in terms of explaining the properties. And in particular, just revisiting this, white and pink in many cases actually acted quite similarly. You can see in the M/P or the action factor plot on the left for SP1, an internal sensor, they're actually quite clustered quite closely together, whereas yellow, as one would expect, absorbing a lot of the blue, and therefore melanopic is low relative to photopic. But again, that's the metric that really is showing the result of what's happening. Internally, we can see the differences between the colors. So again, in all these plots, we'll see a gradual increase across the day. SPO5 is there on the right-hand side. You'll see that collectively. But internally, away from the influence of the external source, you can begin to see how those colors really begin to separate in terms of their M/P values. As one might expect, the blue outperforming the others, white and pink quite close, and then yellow quite deficient in terms of its performance. Of course, the danger in interpreting this literally is that we should then go paint all internal spaces blue and have a very healthy melanopic environment. Of course, this is one of many factors that have to be considered in designing of interior spaces. I'm very conscious of time, ladies and gents, so I'm just going to move on. I'll let you look at this. The last point I'd like to make is revisiting Gall, who, in proposing his M/P ratio, also suggested, because their response function was very close to the color matching function Z, suggested that with existing camera systems and filters that matched that color matching function Z, that you could approximate CCT and therefore M/P from measurements. So what I did was I just took a chance and I plotted correlated color temperature against M/P, and to my surprise, and I've separated external and internal, there's a very, very close correlation. What it suggests, of course, is that if you concurrently measure correlated color temperature, then potentially, if further studies can confirm this relationship, then we can derive M/P without getting into the whole spectral analysis and the complexity that introduces. So just to briefly conclude, we've got a new monitoring system for the study of a range of possible variables, in this a limited number, but in itself highly complicated. A novel data set representing this wide range of sky conditions, wall colors across the day. What was found that in the absence of a direct solar component, there were only modest changes to melanopic content, not as much as might have been expected, as we assumed at the beginning. Where the direct component was present, it was completely dominant in terms of intensity and its spectral character. Wall colors were by far the most influencing variable internally, but where there was a view to the external, and that source of irradiance became dominant. So when we looked internally in the model, we got a very different set of results to when we were looking within the space, but to outside. And finally, the metrics. I think the metrics do need to be looked at very carefully. More people need to be looking at exactly what it is we're measuring, The success of circadian stimulus and EML now succeeded by EDI, I would argue, are largely because targets have been set in publications, and that's what, as designers, we need to work with. But in the absence of those, there's a much wider field, and a melanopic only metric may be something that we might consider, at least at a research level, but maybe practically as well. So this is a link. Again, the slides will be distributed, I'm hoping. So this is a link to the Loughborough University repository where the PhD will be, if you want to scan that barcode, if you have a scanner now, and that'll bring you directly there. And please, if this is of particular interest to anybody, or ongoing work or research, please email me. I'll be happy to have a conversation with you. So thank you very, very much.
Paul, well, thank you. I know from having read your PhD that you had a lot to squeeze in here, and yes,
yeah, sorry about that.
it was a breezy ride, but yeah, I think you managed to get a lot of the important points in there. So, if I think now are the microphones available, so we have any questions? You may wish to signal by putting your hand up.
I think I've lost everybody.
I think they're thinking about it. Okay. Okay, here we go. One in the chat box there. From what you just said, it sounds like blue rooms are more stimulating and yellow more restful. Seems counterintuitive, but goes along with traditional English classic painting of great houses. They had spectrometers all along. Yes.
Yeah, I mean, it's the point I made is, you know, it's pure results like this can often be misleading. We don't want to start painting all our rooms blue simply because it provides a strong melanopic bias. Yes, it might be healthy in terms of circadian entrainment, but there are many other considerations to be taken into account in interior design, really. But yes, I mean, it's there. That's what the results are suggesting at this stage.
Okay, and next one. Is that Ladan? Am I getting that right? The first name. So if you could flip your microphone on.
Yes, hi. Thank you very much for the presentation. It was very interesting. I have a similar question regarding this color blue and yellow. Obviously, you are saying that the blue will reflect more light into space. What about the psychological effect of it? Because obviously we know that blue has got a negative impact on the psychologists, and then has this also been included in the research?
No, I mean, this field is already very active in terms of its transdisciplinary nature, but that is the conversation that has to be had. As I said at the very beginning, some people are beginning to look at this field as if somehow it's almost conclusive, but I would, having gone through this research, suggest that we're still in the early days. This was very much a physical study of a limited number of parameters. Absolutely, the conversation needs to be broadened out to all interested parties, and I would agree. I certainly would not feel very comfortable in a blue room, particularly in the climates that many of us are living in. So the conversation in terms of what actually suits a person in all their needs is much broader. Definitely.
Another thing is, for example, I didn't get that part. Maybe you mentioned, but I didn't get it. That whether when the outside sky is sunny or overcast, does it matter whether the inside is blue or yellow?
That depends on your view within the room. So if you're viewing to the outside, then the sky conditions become the most influencing, the most dominant. Where the sun is penetrating into the space, it dominates. So its spectral character dominates, its color temperature as well dominates. Where you have a cloudy sky, then the internal surfaces will begin to play a greater role. But I would have to say, having come through what I would really say is an initial analysis of the data, because I think there are many observations yet to be made from this, even this small data set. It's complex, and as you saw, there weren't that many variables considered, and yet at the same time, even with the array of metrics available to us, there are still many conclusions to be made.
Thank you.
Okay, thank you. So Clotilde, and then we'll take a text question, and following that, Judith. So Clotilde.
Yes, hi Paul, Clotilde Pierson from EBFL. So thank you very much for the very nice presentation. I have probably two questions. The first one is, at some point you compare the DER, if I remember correctly, calculated with the D65 and with the spectral measurements from the outside. And you mentioned that it would be better to use the outside spectral measurements,
yeah.
Probably. Could it be that the main difference that you get between these two graphs is because the D65 is mainly from the spectrum, whereas your spectrometer was vertical, and so including a lot of, well, I mean, it's not only the sky dome, but it's also the reflection from the ground that you measure in this spectral irradiance measurements, and that impacts the relationship that you had?
No, I wouldn't think so. I'm pretty convinced that the difference between the two plots is as a result of the second plot, where I've used my own measured external data being spectrally relevant to what's happening inside, and the difference it's suggesting is simply the transformations it goes through from source to destination. The problem in the delta efficacy ratio as published by CIE is that what you're looking at is real measurements against D65, and so for every one of those individual measurements, there's a wide range of difference between the source or reference spectrum and the measured, and that's what's causing that difference. Whereas in the second, where I'm using both measured internally and externally, those spectra relate, and the only difference being the transformations occurring. So I would think, I would say 99.9% certain that the external reflections from built or vegetation are not having any marked influence on those results, just simply from measurements taken previously.
Okay. And the other question is, did you measure also the spectral reflectance and spectral transmittance of the materials, or did you just trust what the paint fabricant gave you?
No. So I made a number of sample boards for each of the colors, and they were finished exactly the same way that the panels that were fitted to the model were, and these were brought to the paint manufacturer's laboratory and spectrally analyzed, and it was that spectrum that was used in the software for the analysis. So it was as precise as could be achieved really in the research. So the quantity was known. The spectral distribution for each of those colors was well characterized.
And for the window as well, I guess, the spectral transmittance.
No, the window's interesting. Yeah, I skipped over that one. So we weren't using glazing. What I used was a 4mm acrylic, clear acrylic, to replace it. This is partly safety as well as optics. I have to say acrylic proved to be a very, very useful material. It's easy to scratch, but spectrally, from about 390 nanometers right through to 780, it was uniform.
Okay.
So it proved a very useful material for both constructing the stands inside as well as the replacement window. Yeah.
Okay, thank you.
Okay, if we could take a text question here. So this is from France. So did you mention that the correlation of your data would suggest that spectral measurements or simulation may not be necessary to indicate how well daylit is a space for ensuring proper circadian rhythms?
I would almost go that far. I would certainly say that from some of the correlations observed, there are more simple rules of thumb that could be derived without the need for full detailed spectral analysis. But I would say that this study was exploratory. It is the first of its type. It is in a very specific location and a specific environment. If we could have something similar carried out elsewhere and find the same correlations, then I think I'd be more confident saying that. But right now, I would think, yeah, it is possible from simple Illuminance measurements or correlated color temperature that we can derive certain so-called circadian metric quantities from those. Yeah.
Okay, we'll now take the Judith.
Can you hear me?
Yeah, I think so. Yes.
Okay, good. Thanks very much. It's incredibly important work. I was the one who asked about the yellow and blue room. There's a lot of work done also about by the paint manufacturers in reflectance and absorption, and whether it's a dull surface or a, you know, and whether it's a shiny paint or a very dull paint. And yeah, obviously there's a tremendous amount of work if you're going to follow all of that up. But one of the things that struck me is that in working about how do people experience space, one of the things that's come up in terms of disability and people being able to, you know, see things is the use of contrast and, you know, defining so that somebody with poor sight, you need to define, say, skirting boards and things and doors with different colors and contrast. And one of the things that struck me was that in terms of thinking of blue rooms versus yellow rooms, you know, there are certain classic colors that are used in all the great houses, a certain, not really yellow, but a kind of cream, which is, you know, almost considered a British color. And similarly, there's, you know, racing blue and greens that are traditional and that basically define a room as British rather than French or German, again, because of the spectra. But what would be interesting would be to look at the reflectance where you had, say, a blue room with, you know, a white band and how that interacted, because that introduces in terms of, you know, you're looking at you know, stimulation. And we talk about blue as waking people up. And yet counterintuitively, we think of a blue room as dark or depressing. And yet there are some very classic rooms that are quite exciting because they're dark colored walls, particularly, say, the traditional hanging of paintings on dark red walls with then picture rails and skirting boards in white or something else that sets off. And that has another psychological effect. And I was wondering, in terms of your spectra, whether spectral contrast could somehow be related to the melantropic, you know, index, because it's one of the ways that classically we have painted our walls very, very differently than other countries. And, you know, you can look at photographs of rooms and say that's a British room because it's traditional. And the question is, this is something that's a lived experience. And it would be very interesting to provide, in the kind of scientific work you're doing, some kind of comment almost on where does the traditional come from? And is the traditional actually essentially an experimentally verified, clever and reasonable thing to do that actually works with the way our brains are?
Well, in terms of extending, say, what's been presented today to include the issues you're addressing, I mean, one could see how a full-scale space with subjects that is not only being studied as the reference I made to from where I chose the colors, that was the nature of that study. You could then also include a measurement system and then look at the relation between the physically measured and the feedback from subjects, and you can begin to get some sense. But this is one of the problems in this field, and it's a call that's been made by many, that we need to gather as much information as possible about any single study so that it becomes useful right across the many disciplines that are involved in this work. But at the moment, there isn't a lot of work that I came across, certainly, albeit my bias was towards the technical, that actually combines those two. But there's no reason why it can't happen. And this system that I developed, I am looking at how to just make a mobile unit, make it quite easy to move around, almost out of the pocket. It's not a difficult thing to do. So So that work could happen, but I think it would be very useful to do that. All right, yeah.
I mean, it would be very interesting to do that experiment if you've got a mobile unit in some of the great houses that the National Trust has, and say, you know, what is the experimental, what is the history? Is this, you know, I'm looking at the picture behind your head, and the white door is you know, in contrast to a pale yellow wall. What would the effect be if that wall was blue or, you know, or red with, you know, a painting hanging on it? And these are things that are often, in a sense, I think I'm very conscious of the fact that in many ways we throw the baby out with the bathwater as we start to.
I'll just mention that there is actually some data that we recorded on an ad hoc basis in one of the National Trust properties where I did some work. But I think we need to move on to the next sort of text question. So Sophie, I think, were the experiments conducted without any blinds or shades on the window? That's the case. In practice, how could this be factored into calculations or modelling?
Well, the data set, interestingly, the data set does provide a comparison for computer models. I mean, that's, John and I are kind of maybe hoping that somebody might take a bite of this and say, well, let's have a look at your data set and see if we can recreate those conditions simulated and compare the two to see how they both match. I mean, we have Lark and Alpha building on Radiance as simulation methods. The missing element really is a spectral description of the sky model, and of course there is work going on there. But there is the possibility of applying this data set, not strictly to validate, but simply to compare the two methods to see if they are actually comparable.
Okay, next question from Marshall, I think it is. Could you mention the field of view of the spectrometers and if these were hemispherical like the fisheye, RPI cameras? Was there any cross influence between walls?
Go backwards, cross influence between walls, yes, one would expect so. The spectrometers are fitted with a cosine correction filter. These were made from Spectral, that was the material used, and they were at the front of each of the 5 spectrometers in use. Yeah, so they were cosine corrected. Yeah, 180-degree hemispherical view.
Okay. I think we've answered Roberto's question about the glazing that was used, the acrylic. Okay, so we'll go on to Maria's question. Do you think that different locations, latitude, would have different results in spectral data or the overall sky conditions, direct sunlight, etc.? Could you provide enough information for human-centric lighting that could be used for future guidelines?
I would go so far as to say that we've probably raised a number of issues, but I would like to see this extended further before we'd actually, I'm not sure it's authoritative enough necessarily to influence guidelines and policy just yet. It is, I think in fairness, it's the first such study under a range of daylight conditions. So the fact that it is so new, I think from the point of view of credibility, it would be good that others would carry out something similar. Location, I don't think necessarily that the spectral property, the results would necessarily differ by location, other than if an environment was heavy in particulate that resulted in a markedly different spectra in the sky, i.e. pollution or sound or something like that. Dublin is relatively clean air, so it's quite a clear spectral environment. Where you would most definitely get difference would be early in the day and late in the day, as the sun moves down towards the horizon. That was avoided largely because of the specification of the spectrometer, but I suspect that would show differences and possibly by location as well. Yeah,
I think it's fair to mention that we were both surprised by, how relatively insensitive outcomes were to sky types. We expected sky conditions to be much more influential.
Yeah.